Yeah, good afternoon, everyone. Good afternoon.
Afternoon, ma'am.
Yeah, yeah, now we go with the next module, that is input output organization. Till now, what we have come across, how to write a program, what are means what are the instructions we have and different addressing modes we have, so that how we can write a program. Now we are coming to the next part of it, that is how we are connecting your input and output devices, and how it is recognized, and how the process is going on with respect to input output devices. So in this module, we will study about that thing, and we will even how you are connecting the input output devices via your bus to your process and memory. You are connecting the input devices via your bus. So how this will be taken. So we will study about bus arbitrarization, and how the connection is taken, and how the devices are recognized, and how it is processed. All those things that are coming across in this module. So now we'll start with one. So first thing, how you will access an IO devices. So in this topic, now we'll come across how the devices are connected to processor and memory. So I told it's a bus. So bus will be always having the three carriers. That is, one is with address, and one with the data, and the one with the control signals. So how it will, okay, so n number of devices will be this here. N numbers of device, IO device 1 to IO device N is connected using a single bus to a processor and a memory. So how it will recognize which device as rising, invoked, and which device would to want an access with your memory or with your process. So for that sake, each device will be identified by their unique address. By seeing that address, you will come to know which device is requesting. So each IO device is associated with a unique address. For this sake only, because you won't connect only keyboard, mouse will be also there, joystick will be also there. Those are all input devices. So you are connecting more input devices, so that time to recognize from keyboard, or from mouse, or from the joystick, or because from their address. So to do this thing, the two major things are coming across with that is main memory main memory sorry, that is a memory mapped IO and IO mapped IO. In memory mapped IO, what happens? Both your IO device and as well as your memory will be communicating, or you will be using the same address space. For example, if an instruction is there, move data in comma or not, it means that the content of register buffer or data in is moved to your or not. What is this data in? This is with respect to your keyboard. You will be using this to put in a data. It is a keyboard side buffer which will be storing the data that will be pushed on to your or not. And next and one more instruction, move r not comma data out. It may, what it will move, it will move that r not content, whatever the data in is there, that is moved to your r not. Now the r not content is moved to your data out. So data out will be the buffer at the display unit or an a printer. So whatever the output side will be there, no, that is the data out, and input side will be there, no, that is data in buffer, and one more is data out buffer. The next one is IO mapped IO. It is also called as standard IO, where both the memory and as well as IO both will use different address space. So different address space. In memory mapped IO, what happens? It will use single address space with respect to memory and IO. Whereas in the IO mapped IO, you are using two different address space with respect to memory 1 and with respect to IO 1. So here you are using only two instructions standard, that is in and out, are used to your data transfer. So what happens, see here, uh, while doing this one, what is the main advantage of IO mapped IO means? Only you will use in and out two instruction. So your move, load, store, all the things you are using in the program, that won't used in this. So IO devices will understand in and out instructions. Whereas in memory mapped IO, you can use your load, you can use your store, all those things are used in with respect to memory mapped IO. Whereas in IO mapped IO, you are using only two instructions, that is in and out. Only in and out instructions. So here coming across with an bus, we have come across with that what your address, that you have come across with the address and data line and then a control line. They are connected to your address decoder, control circuits, data status and control registers. In turn, it is connected to input device. So what happens? Address is unidirection. It can give, so whatever the address is there, it will be given to your address decoder and it will decode and gives to your input device. A control circuit is used. So a control circuit is used. So that is bidirectional, and your data transfer, that is connected to your control signal, and your data and your status and control registers are connected to your data line. So now we'll see with respect to each one what the address decoder will do. Whatever the address will be given, that is decoded and given to input. So it identifies or it recognizes the which device means is requesting, that is identified by your address decoder. This control circuit contain the information, whatever the information related to that operation with respect to which address of IO devices, IO device as identified by your address decoder. So first what we'll do, first the address is sent by your address line, that is taken by your address decoder. Address decoder decodes and identifies which IO device it is, and the control signal informs related to that IO device whichever is requested. Then we will come across with the data register. Data register holds the data, means what the IO device is doing, whether it is means it is extracting the data or putting the data. So it holds the data being transferred from or to the processor. So whatever the data has to be transferred or it needs to be taken, the access, so that will be done by your data register. So next is your status register. Means this is necessary information which with respect to your IO device will be there. Status, whether it is ready or not. You will use flip flop, no, flags will set yes or no. Like that, it is also status register, which will be means which will give the information regarding that IO device, that the what status of that IO devices. So next in that only, so the data and the status registers are connected to a data line. You have seen that one. So this data and the status are connected to your data line. So both data line, both are connected to your data line and each having their unique address. So you will come to know data and you will come to know status also. So each will be having their unique address. So there are two types. So data in and data out I had explained in that one. So how it will be done? Data in is nothing but an input buffer associated with the keyboard. So in the first example, with respect to memory mapped IO, I told move data in, comma or not. So with respect to keyboard, associated memory buffer with respect to your keyboard. Next is your data out. It is associated with the buffer associated with your display unit. So interface circuit coordinates this I/O transfer. So when data in is present, when the data is present in the data in that time, it has to rise a flag to indicate the data is present in that, so that it can be moved to your processor. And after processor completes, it has to move to your data out. From the data out, it has to rise then a flag indicating that data has arrived. Now you can display that. So these things will be carried out. So there must be a coordination. Some you will tell it as a synchronization. So that is carried out by this buffers. So three mechanism has developed for interfacing the I/O devices. That is your program controlled I/O and interrupts and DMA, direct memory access. Your program controlled I/O. What it means whatever the program will be there, that is controlling your I/O. Means your software will be there, that is controlling your I/O. Where the processor checks a status flag. Depending upon the status flag, it has to repeatedly check the status flag to activate the request and to synchronization. What's the main drawback of this program controlled I/O? Means you are programmed and you are controlling an I/O. So it has to repeatedly check the status of that device. So the main disadvantage of that, it is repeatedly checking, the time will be wasted in there only. Process has to check every time the status flag of the thing. So that is done in this. So that's the main problem in the program controlled IO. Means less time is taken to data transfer, more time is taken in checking the status of the thing. So that is the drawback of this thing. There are two commonly used mechanisms to implement this. That is your IO device sends an INTR signal. What is this INTR signal? Means it is interrupt signal, interrupt signals which will be sent to via bus only. Whenever it is ready for data transfer, that time it is sending this interrupt request. And the one request is using your DMA controller, where you are directly accessing the memory itself, to the memory or from the memory. So directly accessing to your memory, that is your DMA. Whereas your IO devices, where you are using one more thing, interrupt. You are generating an interrupt signal, and if it is free, it accepts and it performs. So that is your INTR. Whereas DMA, where you are directly accessing his memory, is done. So it is used for your high speed IO devices. So now we will come across an interrupt. What is this interrupts? So you have come across with a function. So in a C, what you will do function. So some broken code will be there, right? Where you will do a call in your main program. Function call is done. It will go and execute and come back. So here, when you are doing with respect to I/O, that time an hardware signal will be generated. I want some joystick is want some input is giving. So it will generate an hardware signal, that is called as interrupt. That is interrupt to alert the process that an IO device is making a request. So after requesting, interrupt signal is sent to your interrupt request lines. So this process can be its own task without need of can check the IO device. All those things won't be done because your request the joystick has requested. No need to identify it as a joystick because it is identified and it has requested. So that will be avoided in this. The request has been recognized by sending your INTA. That is your interrupt acknowledgement. When interrupt request is generated, for this interrupt acknowledgement will be generated. After that, interrupt service routine is called. So that is related. Keyboard it will have different routines. Mouse you will have different routines. Joystick you will have different. So different routines will be called depending upon the interrupt request. INTR is your interrupt request, INTA is interrupt acknowledgement, and ISR is your interrupt service routine. When you press the letter on your keyboard, it will send the interrupt request. Then the process will acknowledge it, INTA. After acknowledging with respect to keyboard, your routine has to execute. That will be done. For example, the printing the routine we are showing here. So you have program 1 and then a program 2. So computer, where you are starting with your instruction. It starts always, it starts with your main executing. So interrupt occurs at I. So when it occurs at I, so it will be holding the address, means you are calling an interrupt. So it will go there and it execute the display routine and comes to your I plus 1. The PC actually contains the instruction I address. When it is jumping from I to your display routine, that time it will store the PC content in your link register because PC will be incremented to I plus 1. Now the PC will be holding the I plus 1 address. After completion of this routine, it has to come to you the next instruction to be executed. So what it will do, PC will be containing I plus 1 that will be stored in a link register. Now your PC will be holding the address of the display routine. So display routine is completed. Written, when it completes and written is executed, that time the link register content is stored back to your PC. Okay, so that next the execution on goes. The process is only the content of PC and the status register. This increases the means while doing this the latency is increased. What is this latency? Interrupt latency, it is nothing but a delay. Latency is nothing but a delay. When the delay occurs, time and interrupt request is received and the start of the execution of ISR. So depending upon this, your delay will be calculated. Time at a time, your interrupt is request is received and starting of the execution of your internet service routers. So that is next is polling. Polling is nothing but you are identifying this device as connected. So that is done by your polling. So information need to be determined whether the device is requesting interrupt is available depending upon the status register. If it is busy, then you will come to know by its status register. Whenever it is requesting any devices, first you will check the status register, then you will serve your interrupt. So following the conditional codes are used. DIRQ, that is interrupt request for your display. KIRQ, it is with respect to keyboard, and KEN, which is used to your keyboard enabling, and DEN, that is used for your display enabling, and SIN and S out are your standard flags. So we have come across two things. One is in and out in IO mapped IO. No? So that is yes in and yes out. So yes in is one when a character is entered at the keyboard buffer. That time it will be set one. When it is 0, when the character is read by the processor, that time it will become empty. So that time it is set 0. So the next character can be loaded into your buffer. Then it is taken, then yes in will become 0. So when the device rises an interrupt request, IRQ will be set 1. This is your register, data in register, data out register, status and a control. So here S in, S out, KRQ and DIRQ, then control DEN and KE. These will be there. So whenever data gets into your data in, S in will become 1. When it is seen by your data out, it will load that data into your data out. When it is moved from data in to data out, S in will become 0 and S out will become 1. S1, S out 1 means indicates that data out buffer is having one character in that. In that buffer, one character is present. That will be known by seeing the S out flag. S out flag will be 1 when it is data is present in the data out. So here is one program with respect to that. So to read one line from the keyboard and store in a memory buffer. That is done in this program. So move hash immediate line that is to your R1. So initially memory is pointing at this. That wait case, that is with respect, that is your label. That is your label. Test bit hash 0 status. So initially nothing will be there, so it should be 0. The status will be holding 0. So test whether yes in is 0. Yeah, whether status of yes in initially what it will, no data is present, so it is 0. So branch you are doing, branch install is 0 is because you are seeing a group of characters make a word, no? So character wise you will be loading. So wait for k means waiting for character to be entered from your keyboard. To be entered from your keyboard, it is waiting. When you will start to enter, then that will be moved from data into data into R1. So read the character. You are reading that character. So this will be done here. Then test bit, you will now when you have read the data and it is stored in a data in and your yes in is set 1. So now that display unit come to know that data is arrived. So that has to move to your data out. Yeah, so that will be chucked here. So test bit hash 1 status test yes out branch is equal to 0. Wait for the display to become ready. So display unit is getting ready. Now you will move the content of R1 to your data out. Means you are sending the character to display whatever is stored in your R1. So now you will move R1 to your R1 means store the character and advance the pointer. Pointer will be incremented. So you will increment. That is your auto increment is done. So comparing this, check its carry return all thing is done. Again wait k. Again your branching is done. The label it goes get another character and it will goes on. Move then otherwise send line fed means that is the end of the line and call your processor. So you are calling, you are going to your main program. So this is the program. Next is your interrupt vectors. So interrupt vectors, vectored interrupts means requesting an interrupt by identifying its directly to a processor means here directly the processor is identifying the interrupt. So that is done here. It can be done. How it will be done? How directly you are identified by a processor? by sending a code that is a 4 to 8 bit code to a processor. You have to directly, that will be directly sending to the bus, the processor, whichever the device is interrupting, it is directly connected to a processor. So it will be sending a special code which will be of 4 to 8 bits. So code supplied by the device may represent a part of the static address of the interrupt service routine that is to be done. The remainder of the static address is obtained by the processor based on the other information. So 4 to 8 characters only starting this thing will be sent. The rest will be processor will be identifying uh, by the range of memory address and interrupt service routine and the location. Using that location pointer by the interrupting device is used to store the starting address of the ISR, interrupt service routine. So then IO device organized in uh, that is done. So you identify now. So now you have n number of devices connected in it. So when you are connected to n number of devices, that time which your priority you have to set, because all will be having won't be having the same slot of time. Same slot of time, same slot of time. So if keyboard as means each device will be setting a priority depending upon this, the priority that interrupt will be served. Some means higher priority, lower priority will be set for that one. An interrupt request from a higher priority device is accepted while the processor is executing the interrupt service routine of lower priority device. So first the higher priority will be served, then the lower priority devices is served. So priority means what's the level is, how you will decide this is the higher priority or the lower priority, that can be changed, that can be changed by your program control. So which one is having higher priority, that is decided by the program. So priority level of the process is the priority of the program that is currently being executed. So which is the, depending upon that it will be done. When the processor starts executing the interrupt service routine of a device, its priority is raised to that of the device. So when it is executing, its priority is right. So really, so that seeing that priority, it will execute. Here, what happens when you set the priority? There is one drawback. The lower priority won't be served until this higher priorities will come. So what happens? Starvation will occur, and until at last it will be done. Because I want to complete the task within 1 hour, but within 1 hour I has been not served. So that time what happens? The time out will occur. When the time out will occur, that time it will be happen. So you have to see that also, and you have to design that also. So with respect to this, we will join next class. I will be telling about this, how you will maintain your priorities, how it is be identified, and how you will change these priorities. So all those methods will come across in the next class. Okay, have a nice day.